For centuries, the question of whether other civilizations exist among the stars was a matter of pure speculation. In 1960, that speculation encountered the first attempt at measurement using the tools of modern radio astronomy. Astronomer Frank Drake launched Project Ozma at the Green Bank Observatory, turning a massive 85-foot radio telescope toward two nearby stars, Tau Ceti and Epsilon Eridani. He was listening for a signal that would prove we were not alone. Drake and his team spent 200 hours manually tuning receivers and analyzing paper charts. They were searching for a specific frequency, the 21-centimeter line of neutral hydrogen, where they believed an alien civilization might choose to broadcast. While the search found only silence, it triggered a meeting of minds. In 1961, Drake gathered a small group of specialists, including a young planetary scientist named Carl Sagan, to discuss the feasibility of interstellar communication. To structure the 3-day conference, Drake jotted down 7 variables. Multiplying them together created a probability argument for the number of detectable civilizations in our galaxy. This sequence provided a framework, organizing a massive, abstract mystery into smaller scientific questions. Scientists visualize this equation as a cosmic funnel. Each variable acts as a filter, beginning with billions of Milky Way stars. The first filter is our star, the rate at which stars suitable for life are born, providing the energy necessary for biological evolution. In 1961, Drake's team estimated 1 new star per year. Today, we look at the rate from 4.5 billion years ago, when our sun was born, to account for the time required for an intelligent species to emerge. The next variable, FP, represents the fraction of those stars that host planetary systems. This chart details the modern simulation loop used to estimate exoplanet populations. Data from the Kepler survey and simulators like EPOS show that planets are nearly ubiquitous. We now estimate that almost every star in the galaxy hosts at least one world. We then look for NE, the number of environments per solar system that can support life. Modern astrobiology has expanded this count. Beyond Earth-like planets, we now search for life in the subsurface oceans of icy moons, and even within the organic chemistry of asteroids and comets. Even with conservative estimates, the astronomical side of the funnel remains incredibly wide, suggesting trillions of potential habitats exist in our galaxy alone. The math becomes more difficult as we enter the biological variables, starting with FL, the fraction of habitable worlds where life actually originates. We know the chemical precursors of life are common. However, researchers like Melvin Calvin noted that while the transition seems probable, we have yet to prove how often it successfully occurs. If life does take hold, we must consider Fi, the fraction of those worlds where life evolves to become an intelligent civilization. Intelligence took billions of years to evolve. If that process had been 30% slower, our sun would have sterilized Earth before humans emerged, proving the window is narrow. We then reach FC, the fraction of species developing detectable interstellar technology. Modern SETI searches look beyond the 1961 focus on radio waves. We now scan for a variety of technosignatures, including the massive structural presence of Dyson spheres or the movement of artificial interstellar probes. Finally, we face the most significant variable, L. This is the length of time a technological civilization persists in a detectable state. If a civilization survives for millions of years, the probability of contact is high. If they routinely self-destruct within centuries due to war or environmental collapse, the galaxy remains silent. This variable creates an immense mathematical bottleneck. When we multiply trillions of planets by a very short survival time, the number of civilizations existing at the same moment as us drops toward 0. Because the galaxy is billions of years old, civilizations must last for a significant fraction of that time for their signals to ever overlap. Without a high value for L, all the planets and life in the universe will never be detectable to one another. This bottleneck leads to the Fermi Paradox. If the number of habitable planets is so high, why have we found no evidence of anyone else? One proposed explanation is the Great Filter. This theory suggests that one of the steps in Drake's equation is nearly impossible to pass, acting as a lethal barrier to any emerging civilization. If the filter is behind us in our evolutionary past, then the development of intelligence is a statistical miracle. If the filter is ahead of us in our technological future, then most civilizations reach a certain level of power and then inevitably vanish. To find the answer, astronomers are moving beyond targeted searches. We are now scanning the entire sky for anomalies and unexpected signals. Next-generation telescopes and AI-assisted data analysis allow us to process petabytes of cosmic noise, systematically checking variables that were once just guesses. While the Drake equation cannot yet provide a definitive number for n, its value lies in its ability to focus our exploration. It remains the primary guide for our search, identifying the specific biological and technological markers we need to find to finally answer the question of our place in the universe.